Hello, my name is Evan Campbell. Today we're going to be going over the Spectre Attack from seedlabs. So to start off, we're just going to talk about what a Spectre Attack is. So Jan Horn was one of the founders of the vulnerability along with Paul Croker, or Kosher. Jan Horn was a Google Team Zero member and Paul Kosher is a cryptographer. So they found this vulnerability in 2017, but it was public information in 2018. This vulnerability is common for mostly all modern CPUs, and it is mainly a hardware problem, not a software problem. So this vulnerability utilizes branch prediction and speculative execution. It can The main goal is that it will just be able to obtain data from other running programs that the user is running. So what is speculative execution? Speculative execution will occur when you have an if statement. Basically, the CPU would try to be ready for the outcome that it thinks might happen, so it'll just prepare for it, and that way it'll try to be faster. What about branch prediction? Well, branch prediction is basically just the same thing. When a conditional operation such as an if-else statement needs to be processed, the branch will just guess which one is most likely to be met, and it'll then kind of just preload everything going down that path. This is very useful in terms of speed for computing. Obviously, if the CPU branch prediction is correct, then everything will be preloaded and you'll be good to go. However, if it's incorrect, then everything that was loaded won't be used, and it'll go to a place called the cache. So speculation and branch prediction may seem harmless and really beneficial for speed, but most modern CPUs will have a cache, so they can basically the cache is made so that they can call on that again if the program runs those codes, so the memory, like, they don't have to access the memory, saving a lot of time. However, due to the branch speculation exploits, the leftover parts, if it is false, would be left in the cache. So if you are like running a program and you have everything after, and it kind of thinks it'll load all that, so it'll load everything, but if that if statement doesn't happen, all that will just be sent to the cache, so all your code will just still be there. So with the cache containing the what if portion of the code that wasn't true, threat actors can exploit that address in the cache using kind of like a side tunnel, and get their code to run even when it's false, leading them to be able to run out of order executions during a race condition. So let's see how it works. We're gonna go into our 16.04 virtual machine in Linux and try to do this vulnerability. Alright, so now that we're in our seedlabs here, our virtual machine, you can go ahead and open up Firefox and just kind of get rid of everything. So once you have your seedlabs up, obviously you can have the description. There's where you would download the VM. There's some hands-on approach videos. They weren't very useful to this topic, as you do have to purchase a Udemy course to be able to watch them. So if you don't want to spend your money, I wouldn't recommend that. And then all the files that you need are right here in the zip folder. So if you want to go ahead and click on that, just open it, and it'll ask you where you want to extract it to. So I've done this in documents already, so all my updated codes are in there. For now, I'm just going to save it to desktop and start fresh. So we've extracted it. Close. So now we can go ahead and open up our terminal and start trying to exploit. Just change the name really quickly. There we go. So first off, we want to make sure we're in the right directory, which we're not. So we just need to go into desktop here. Now that we're in here, we can see that we have this folder. So again, we're going to want to change our directory to Spectre Attack. Now that we're in here, if we go ahead and list all of our files, you can see that we have them all here. So we have Spectre Experiment, Spectre Attack, Spectre Attack Improved, the cache time, and the reload time. So to start off learning about the cache, we're going to look at the cache time. Oh, I forgot the uppercase. So we're just going to go and quit this. Alright, so looking in cache time, this lab is going to have an array, 10 long, or 10 times the 4096 value. So basically what this is doing is it's going to initialize the array for the length of 10 there. So each time it's going to make another one. So we're going to get like a full array here. And then in here we're going to push these into the cache. So just for demonstration, when we run it later, we can see how much faster it is and how many less cycles it takes. And then here, we're just going to be printing out the cycles so we can see it. So I'm just going to go ahead and back to terminal. So we can go ahead and compile. So it's important to use the march equals native here if you want these attacks to work. So march attack, we'll just call it CT for simplicity. And then the cache time.c. So now we can just go ahead and run our executable. And as you can see, it's printed out those 10. So obviously 0 to 9 is 10. Here we go. We have longer CPU cycles and everything except for the 3 and the 7, which is where they pushed those values into the core. Not the core, the cache. So as you can see, it is much quicker than the rest of them, and this is how we can see if something's in the cache. So after that, we're going to want to talk about the flush reload.c. So we can go ahead and do the VI. So the way that this attack will work is it flushes everything out and creates a whole new array. Then it'll reload everything kind of back in, and that's how you'll be able to see your vulnerable bits. So now we can go ahead back, and this is what's called a side channel. Kind of what we're using here, the flush reload C, is kind of just operating as a side channel. So we're going to go ahead out of here, and we can just compile it, just like we did the last one. So we'll name this one FR for flush reload. So now that we have it compiled, we can go ahead and run this. So as you can see, it's telling us that the secret here is 94. So again, if we go back into our VI for the flush and reload, we can see here that we do have the secret labeled as 94. So we can go ahead and change that if we want. So for purposes, we'll just make this 83, because later on we'll be using 83 as the secret. So yeah, we'll go ahead and save this. And if we recompile it and just run it again, it'll tell us that our password is, in fact, 83, or the secret, I guess. So now that we have an understanding of how these few files work, we can go ahead and move on to an example of the out of order execution and branch prediction. So we can go ahead and do the Spectre experiment.c compilation. So we'll just use SE for Spectre experiment. So we can take a look at it really quickly. So looking here, we're using that flush technique that we had just done to basically print out that secret, and yeah. So this will be using an out of order kind of execution. So we can go ahead and exit here. So we do have it compiled, so we're going to go ahead and just run it. So SE. As you can see, it's telling us 97. We'll go back in here and change the password. Down here where it says victim, so we're running victim. That's our kind of just holder program. That would be that if statement that we were talking about earlier, where the speculation begins. So if we go ahead and make this 83, it'll just tell us that our secret is 83. So again, we'll just compile it. Oh, I don't remember typing that. Weird. Okay, so we're just gonna go ahead and delete the rest of these A3s. So now we'll just save it and hopefully that works. Yep. So go ahead and just run this. As you can see, the secret is 83. So now we know that this works that way. We can go ahead and move on to the Spectre code itself. So just regular Spectre Attack. So what we're gonna do is we're going to go ahead and compile our Spectre Attack. So we have Spectre Attack here. We'll just call it SA. So now that it's compiled, we can go ahead and run it. And as you can see, it does give us 0 this one time. And it gives us 83. That is because there could be some false positives. Every now and then it might not work. So to fix this, we can actually have an advanced method where we will have to add a loop. So let's go ahead and take a look at that code. So we'll go ahead and look at our Spectre Attack improved. So looking at it now, there isn't much difference to the main part of this code. However, once we get down here, this bit of code here will be kind of running that previous attack that we did, where we got 0 and 83 over and over again. This is kind of a way to fix the background noise, more or less, the bunch of zeros that were popping up, the false positive. That was kind of messing with our results. So if you run this 1,000 times and we just kind of tally up which number, so in the array, that's where those values are coming from. So up top here, we have this, we have an array right here. scores, we have an array 256 values. So the first bit in that array would be scores 0. So that is where that 0 is coming from. If that was pinged as the fastest the most times, then we would get 0. However, if we have 83, which is in our actual secret at this point, then we should be getting that 83 returned as our secret. So the way to fix that, again, is just basically running it over and over again, 1,000 times, and then seeing which array value gets pinged the most. So we know it should be 83, but there are actually a few errors with this code. So if we go ahead back to our terminal, we can go ahead and compile this. Let's call it SAI. Huh. That is weird. Go ahead and download the file again. Maybe we accidentally edited it. We'll go ahead and put it in desktop. Yeah, okay. So we have them in desktop here. So yeah, we'll go ahead back and try this again. Yeah, okay. So our file is there, Spectre Attack. So we're gonna go ahead. Okay, so now that we're back in here, we can go ahead and recompile that program. Okay, and it worked. So obviously those weren't the errors that I was talking about when I said the code had a few errors. So if we go ahead and run this, you will be able to see what I mean. So right here, it has said that the secret value is 0. So the number of hits is 1,000. So basically the number of hits is saying how many times that place in the array was pinged as having the cache. So obviously if we do this, every time it's going to be 0. And we know that that is incorrect. We know that the correct answer is 83. So I've already fixed this in another directory. CD. So if we go ahead over there, yep, CD. So looking in here, these are all the files that we had earlier. So we want to be looking at this improved.c. So we're going to go ahead and use VI to open it up. So let's take a look at what we found was wrong here. So we're going to go ahead and go all the way down to the bottom. Most of the stuff commented out is how I used to debug this. I started off printing out results and seeing, maybe it was just a weird error that there was not the right type there. So looking through, I was going through this for loop here for a bit, working in the debugger with it, but there was no errors in here. This code is perfectly fine. So is the int max there, obviously. So then I kind of started looking towards the other part of int main. So more specifically, this was fine. I looked through that, and then I wanted to look through the reload side channel improve. So I came up here. I was looking through the the list. I came through here. I didn't know if they were getting the right values. Maybe this if statement wasn't working out. Basically, this is just saying, like, if this is below our cache hit, which we have set to 80, then it'll add one to that array score. So that's basically where the hit would come from. So I used a print statement just to see if it was actually in fact going in there, and it was. So I just wanted to make sure that that if statement was working properly, and it was. So that was fine. So then I started printing out the scores here and the scores array down at the bottom. So I used a for loop to print out the scores array, and what I found was, actually I can just show. We go ahead up here. Yeah, okay. So if we go ahead and save this, we can compile it, and we can go ahead and run it. And so again, it's still not working yet, but if we go ahead and look through here, this is the 256 array blocks. So as you can see here, this one was pinged 35 times as being under the cache threshold. And if we keep going up, then we'll see where we started, and boom, right here is where the main issue is. So for some reason, this value, the initial value for the array, so score 0, is at 1,000, which is not what we want. So we can go ahead and just clear this up so it looks better. We'll go back into our VI. So now that we know where this issue is, we can just investigate further. So you can print out in here kind of like what score 0 is, and what you actually see is pretty interesting. So I don't know if that is going to work. Yep, okay. So looking back in the SAI, obviously we have our code here that's printing out earlier. 67 times was pinged. But if we look here, this is the counter for kind of our code. So this is what is going into that first array block every time. Obviously it goes all the way down from 1 since we run this code 1,000 times. But so now that we know that that is where that issue is, if we go back into our VI here, we know that for some reason this counter right here going from I to 1,000 is messing up our first value of scores. So now to originally fix that, you could add this if statement, basically just saying like, if that ended up happening, just regard it. Like, it's very improbable that it got pinged all of those times, and for a fact we know that it shouldn't have been. So again, if you use this if statement, that should work. So go ahead and comment this out, because we don't want to look. We don't want to look at that for loop being printed over and over again. And I think there's one more up here. Yep. Up in the reload time. So we go ahead and comment those out. We can go back to the beginning and just recompile it, run it, and as you can see, it worked. So we have 83 there. I also uncommented that high earlier. That was just to make sure it went into the if statement. So the secret value is 83, which is correct, and number of hits is 7. So we can keep doing that. It's going to work every time. Yeah. So if we want to go ahead back into our editor, I felt like there was a more efficient way. So if we go ahead and delete these 2 lines right here inside that for loop, let me go ahead and save this, compile it, and run it. So again, it's working perfectly fine. That was just another way to do it. I feel like it was more efficient. You just add a you just reset that value once it goes into that for loop. So once we go into that array, we don't want that value of I carrying over. So we're just going to reset score 0 to 0. And that way it has worked every single time. So now for the last task of this lab, we actually want to print out that whole string. Now you could edit this file, but I had already messed with it enough and decided to kind of rewrite another one. So using that, where did I put you? Documents, Spectre Attack. So we named it Full Attack. It's just basically another line of code. Again, you have your victim code here, kind of the same thing. And then basically throughout you're going to be using flush and reload again. And as you can see, we have our threshold here, and the password that we are trying to guess is some secret value. So this is what we want to be returned to us. So we go ahead back to our terminal. We've already compiled this, so we can just go ahead and run it. It's called Full Attack. So if we run that, as you can see, it goes in and it prints out that password for us, some secret value. So that was a walkthrough of the seedlabs for the Spectre Attack. Thank you for watching. I hope you enjoyed.